Good morning, friends. Uh, Today we are going to discuss the 8th experiment of digital signal processing lab. Now here I am giving you the experiment that effect of different windows on FIR filter. Up till now we have learned about the FIR filter, and in terms of FIR filter there is different ways of defining this FIR filter. So out of that there is a windowing concept. So with the help of this windowing concept you can find a lot of benefits are there. So that's why the FIR filter design is carried out in this experiment with the help of different windows. Okay, so see, here I am showing you how you can use these different windows for designing of the low pass and high pass filter. First of all, we will discuss here which type of windows are present here. So see, there are different types of windows are present with the design of this FIR filter, like a rectangular window, Hemming window, Henning window, Bartlett window, Kaiser window, and many more. There are number of windows are there in the world of the digital signal processing. There are different kind of windows are coming under this FIR filter, but out of that some few are listed for your curriculum point of view, right? So I hope in that you are knowing that every windowing having their its own expression for declaration of this function. Okay, so that's why the rectangular window function will be declared by omega or w of n is equal to 1. Okay, it is for the value of n from starting from 0 to up to m minus 1, and its value will be 0 for other cases. Similarly, if you talk about the ham window, then its expression will be 0.54 minus 0.46 cos of 2 pi n by m minus 1. Okay, and it is valid for n is equal to 0 to m minus 1, and other cases it will be 0. Okay, I hope these expressions will be with you in your notebook. Okay, you already did the design. Here one comparison is shown between these rectangular Bartlett, Hamming and Henning. Okay, everyone will have its own way for calculation, so that's why every windowing technique will have a response. Okay, that will be different to others one. Okay, so here we will go for the design of this FIR filter. Okay, we will see with the help of program how you can able to design. Now this experiment is getting divided into 4 sections. So out of that, first section and second section is based over the low pass filter design, and third and first I hope first is based over the low pass filter design using rectangular window. Second section is based over the high pass filter, high pass filter design. Then again the low pass and high pass filter design using other windows. So initially I talk about the rectangular window, and then we will go for the Henning windows, right? So we will do the comparison between the different kinds of windows using this FIR filter. Okay, so you will get idea from this experiment, you will get idea about how to use windowing functions, okay, with the help of MATLAB. Okay, in most of the cases when you are going for the real time application development, that time also you need these types of windowing function utilization. So for that point of view also you will get an idea how you can use these functions for the calculations. Okay, if you are implementing any application using DSP, then it will be very better for you. Okay, so see, the first section that I am telling you here, this is a low pass filter design using a windowing function. See, first three statements: clear, clear all, clear close all. Okay, then these parameters are described like n is equal to 20, F is equal to 200, Fs is equal to 600, F is equal to 1000. Okay, so here the passband frequency, stop band frequency, and F is a total frequency. Okay, so F is maximum because of here the passband and stop band we will decide. Okay, N is the total number of order of the filter, right? So here four parameters that I define here. I hope you got the idea from the FP and FS. FP is a passband frequency, FS is a stop band frequency, N is the order of filter, and F is the frequency. Now here we will calculate the passband omega and stop band omega. Okay, so that's why omega p is calculated by 2 into fp by f. Okay, so that's why passband frequency divided by the frequency into 2. Similarly, the omega s is calculated by 2 into fs by f. Okay, so these two formulas are used for calculating the passband and stop band ripple. Okay, then we use here a window function, so that's why that window function you can able to declare with the help of this box char. Okay, so here its value is 1 for 0 to m minus 1, and it will be 0 for other cases. So that's why here the window is calculated with the help of this box char in bracket n minus 1. Okay, n plus 1. Okay, it is a function. Okay, similarly here omega n is a frequency. Okay, it is calculated with the help of this 2 into fp by m. Okay, now n is known, omega n is known, and windowing is known, so that's why we will go for the filter FIR filter design. So that's why FIR filter will demand these three things: n, omega n, and window, which window we are utilizing. Okay, so that's why from that you can able to find out the coefficients b. Okay, so once you got the coefficient of b, you can able to find the magnitude and phase plot. So that magnitude and phase plot will give a clear idea about the passband and stop band. So that's why frequency name function is utilized. Okay, in that we will pass the parameter b. Okay, once you pass it, you will get the h and w. H will representing magnitude and w is representing the phase. Okay, so that's why here in the subplot we go for the plotting that magnitude. Okay, so for that here magnitude plot point of view, here in plot function x and y is defined. Okay, so that's why x is defined with the help of w by pi. Okay, because the whatever the frequency that will not able to accommodate in the given graph. Okay, so that's why we are going to do the managing of that graph. Okay, or to limit over the x axis and y axis, this technique is adopted, like w upon pi. Okay, so that's why that w is get divided by 3.14, and again here that absolute value will be quite high one. So that's why it will not showing the graph in proper fashion. So that's why to make it in proper fashion, here absolute value is means magnitude plot is passed to the logarithmic function, and again it is multiplied with 20. Okay, so that's why this particular mathematical expression will be put for the plot function. Now once you have idea about the x and y, okay, they are plotted over that graph. Okay, then here labeling is required, so that's why x label, y label, and title is given. Similarly, the in terms of phase plot, the same criteria is adopted. Okay, only here the plot function will be written in the another way. Okay, for phase plot it is not necessary to redefine the mathematical expression, so that's why it is written as angle in bracket of h, and on x point of view, here again the same concept was here, w by pi. Okay, so again do the labeling, that x label, y label, as well as titling. Okay, now this is about the entire code. I hope you got the idea about this code. Okay, somehow if not getting idea, okay, then no issue. Actually here it is very simple. All the parameters you can easily read it. Okay, just by just observation you can able to understand all the things. Okay, just I run the program. Okay, you once I run it, you will get an idea how the passband and stop band are get separated in the magnitude and phase plot. See, in terms of magnitude I have mentioned the 400 and 600 will be the passband and stop band frequency. So that's why here in terms of passband you will get a flat response, but in terms of stop band you will get a ripple. So that's why that ripple is saying you here the stop bands, right? So the magnitude plot will give a clear idea about the low. It is a low pass filter. Okay, but from the phase response it is not giving you a clear idea about that it is a low pass filter. Again, it required some kind of mathematical expression, so that's why it will get narrated in proper fashion. But I think it will be quite enough for declarations. Okay, both graphs are very beautifully represented in this graph. Okay, so that's why I hope mathematical expressions are quite enough for representing these things. So this is about the window low pass filter. Okay, so I hope you run this program with your MATLAB. Okay, and check whether you are getting the response in this fashion or not. Okay, so also I am telling you here, you try to change the values. Okay, with the help of values you can able to understand what the effect will be drawn over the implementation or design of this FIR filter. Okay. Now second experiment that we look here. Here only slight change in the experiment is that function is changed. Okay, in a earlier program you seen a box char name function is written. Okay, so here the second experiment that I am telling you here, everything is same, only the value is changed, that function is changed. Okay, so instead of box char type function, here barlet name for window is used here. Okay, see, whole program just if I switch it. Okay, if I switch from first to the second one, okay, only the change is the program. Okay, only the change is the function. Okay, very simple, not much difficult. Okay, so here uh, second program, again I am telling you here how you can write. Again n, fp, fs and f are defined. Okay, then wp and ws are both are calculated. So the formula is for wp is 2 into fp by s, and for ws it is 2 into fs by f. The new thing is here declaration of this barlet window. Okay, so that's why window is equal to barlet in bracket n plus 1. Okay, now once you got the window parameters, you can able to calculate the omega n. It is calculated by 2 into fp upon f. Okay, I hope the same statement is repeating again. Okay, sorry, in earlier it is wp and now it is wn. So wn is calculated. Once the wn is calculated, okay, you will able to pass this value and wn. Okay, and window. Okay, high is just for name. Okay, so FIR filter is declared FIR1. Okay, b coefficient are get calculated. Once you pass it to the frequency, you will get the magnitude and phase, and the magnitude and phase plot is plotted, right? I hope it is very similar to your earlier one. So I directly go for the running of the experiment. See, if you run, you will get the output as observable. Okay, here you can see the response is for a high pass filter, not low pass filter. You can see near about at 600 hertz you will get the flat response. Okay, and below 600 hertz you will see there is a pause stop band. Okay, in magnitude plot you will see it is observable, and in terms of phase plot you will see the entire wave is similar. Okay, there is no huge change in the difference, okay, between the pass band and stop band. But for your identification, magnitude plot is enough for okay, for your understanding. I hope this will be enough for you, your understanding, right? So just I am closing this graph. Now I am switching over the third one. Now in terms of third one, again only the change is that instead of Bartlett, okay, here Hamming window is declared. Okay, and the rest things will be as it is. Okay, there is no huge change. Okay, just I run the experiment, you will see how the graph is observable. Here it is for low pass filter. Okay, so here up to 600, okay, hertz it is a pass band, and after 600 it is stop band. Okay, so magnitude plot is very fantastically defining the difference between the pass band and stop band. But the phase response, there is some how difference. Okay, in pass band you can see the larger pulse width, and in the stop band you will find the shorter pulse width. Okay, so these things are observable using the pass band and stop band side. Okay, this is about the third one experiment. Okay, and last one, fourth one is defined with the help of Hamming again. Okay, here we are going for the high pass filter design. Okay, just I am showing the I am just executing the program because everything is same. Okay, only difference is here the instead of low pass, here it is a high pass filter, right? See, you will see the magnitude and phase. Okay, near about at 400 hertz it is a pass band and stop band separation, so that's why below 400 it is a stop band, and after 400 it is a stop pass band. Okay, so uh, you can see it is very clearly represented at 400 hertz. Okay, above 400 you will find a higher one spike, and below 400 it is a lower spikes. Okay, so these things are enough for your understanding. This is about the 8 experiment. I hope you are doing it well. Okay, try to run it over your MATLAB. Okay, and go through it all experiments. Okay, also just do any changes in the parameters value. Okay, you will see the change in the magnitude as well phase plot. Okay, you will change the pass band and stop band frequency also. Okay, also you can go for the band stop as well as a band pass filter. Okay, actually I already given you idea with the help of help. Okay, so try to do it. Okay, so by your permission I am quitting these experiments. Okay, so thank you very much for watching these videos. Okay, as well as in case if you have any doubt, you can WhatsApp me. Thank you very much.